Optimization problems in calculus can be tough, especially when they don't really represent a physical situation and you're just given some relationship between two numbers that you have to try and find. So in this case, we're going to be going over an example, which is actually from my weekly live stream that I'm doing every Monday night at 5 Pacific, 8 Eastern, where we know that we have two numbers that we're trying to find who have a specific sum, and we're trying to minimize the sum of their squares. So it's a little bit of a weird case, and I wanted to show you this example because you can use this exact same process to solve pretty much any optimization problem you're going to run into. So without further ado, let's go ahead and jump into the example. So the example we're going to be going over here is the sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? So again, what we want to do is think about the five kind of main steps that we're going to go through with all these optimization problems. First of all, we want to just take a step back and think about our problem and what it's asking and what it's telling us that we already know. So first of all, it's telling us that we again have two positive numbers and we know that their sum is 16. So notice it's telling us right off the bat that we only want to consider positive numbers. We're looking for two numbers and they're going to be positive. And we want to make sure to find the smallest possible value of the sum of their squares. So again, right off the bat, we know we have two positive numbers. We don't know what they are, but again, we can kind of just say x and y. We know they're positive, and we know their sum is 16, and we know what we're looking for. We're going to consider the sum of their squares. So that's really all we want to kind of figure out for step one. Step two normally would be to draw a picture. Again, in this case, we don't really have something that the picture can be drawn. A lot of times that's going to be describing a geometric shape. Could be a variety of other things, but there's not really anything to draw here. So we can kind of skip our second step. Then the third step to these optimization problems is going to be to write out our equations. So we're going to have the equation that we're trying to optimize. So we're going to have some quantity, which we'll call Q, which we want to either make as big as possible or as small as possible. In this case, the thing that we're trying to get as small as possible is the sum of their squares. So the sum of their squares is just saying, first of all, what are their squares? Well, the square of x is just x squared, and the square of y is just y squared, and we're trying to make their sum as small as possible. So if we take x squared plus y squared, this represents the sum of their squares. Okay, so then the other equation that we need to make sure to come up with is our restriction equation. So what sort of equation is actually restricting these x and y numbers that we are looking for? Well, we are told that the sum of them is 16. So basically we know x plus y is 16. We also know they're positive, so we can also say x is greater than 0 and y is greater than 0. That's not going to really come into play until the end. In case we get negative x's and y's, we know that we can disregard those. But these are going to be the two equations that we want to use. Okay, so then what we want to do is we want to take our restriction equation and we're going to solve it for either x or y. So let's just go ahead and solve for y. In this case, it's really not going to matter which one we solve for, but we can just kind of randomly pick y. So we would just minus the x over to the other side and get y equals 16 minus x. So then once we've taken our restriction equation and solved it for one of our variables, we would take this and plug it into our optimization equation for the variable we just solved for. So we know that y equals 16 minus x. We want to go back up to our optimization equation and replace the y with 16 minus x. So doing that is going to give us q equals x squared plus 16 minus x squared. So do be very careful here. In our optimization equation, we had y squared. We need to make sure to square this whole thing that y is equal to. That 16 minus x needs to be in parentheses or we're going to get the wrong thing. Okay, so now let's think about 16 minus x all squared would be the same as saying 16 minus x times 16 minus x. So then we can FOIL that out to kind of simplify things for us. So 16 times 16 is 256. So we'll get 256 minus 16x minus 16x from doing that and that, which will give us minus 32x. And then negative x times negative x gives us plus x squared. Okay, and then we can simplify this by combining our like terms. So we get 2x squared minus 32x plus 256. So this is now the function or the equation that we want to optimize. So let's go ahead and just say that this is going to be our function f of x. And this is the thing that we want to either minimize or optimize, depending on what the question's asking you to do. In this case, we want to make sure the smallest possible value, because it said right here, smallest possible value of the sum of their squares. So we're trying to make sure that this equation that we're optimizing is as small as possible. Okay, so to make sure something is as small as possible, we need to first find its critical numbers, which means to take the derivative of the function, and then we'll set it equal to 0. So we'll take this using the power rule, bring the 2 down in front. 2 times 2 is 4. Lower our power by 1, which just makes it x to the 1, which is just x. Derivative of minus 32x is just going to be minus 32. The x basically falls off. And then the derivative of a constant is 0. Okay. Then to find the critical numbers, we set this equal to 0 and solve for x. So to get the x by itself, we'll add over the 32. Then we'll divide both sides by 4, giving us x equals 8. So in this case, there is only one critical number. Typically in these optimization problems, if you do get only one critical number, that's going to be the one you go with. It would definitely not be a bad idea to confirm that by doing either the first or second derivative test to confirm that that gives us a minimum rather than a maximum, since we are trying to make this as small as possible. But just to kind of save time here, I'll leave that up to you if you want to, confirm that just to make sure. But now we know our x, so we know one of our numbers. And in fact, this is a positive number. So we know that it meets the fact that we have to find two positive numbers. And now what we can do is we can go back to this equation we found here when we solved for one of our variables in terms of the other one. If we know x equals 8, we can find y by plugging x into this equation. So we get 16 minus 8, which is 8. So if x equals 8 and if y equals 8, that is going to be the equation where we know that their sum is 16, 8 plus 8 is 16, and the sum of their squares is as small as possible. If we picked any other numbers besides x equals 8 and y equals 8 that added up to 16 and then squared them and added them together, found the sum of their squares, it would be bigger than it would be with these. So that is going to be it for this problem. That's how you apply those 5 steps. Well, I hope you found this video helpful. If you did, please be sure to hit that like button down below. I'll be doing a weekly live stream every Monday night at 5 Pacific, 8 Eastern, like I said. But be sure to hit that subscribe button and bell icon as well so you're notified when I'm going live each week and you can come, maybe even get some of your own questions answered. Hope to see you there.